Click the bell icon to get latest videos from Ekeeda.
Hello friends, I welcome you all to this video. We are with the 12th chapter of microwave engineering, where a family of microwave passive, that it means microwave components, we have been addressing so far. So after E plenty, H plenty, magic T, hybrid rings, we have come to the directional couplers and the special case of two-hole directional couplers. Recently we have addressed into the previous video there. Now based on to the knowledge regarding the behavior of the directional coupler, in this video let us have the derivation for the scattering matrix, simply called as S matrix for the device. So here we begin with our topic, S matrix of a directional coupler. So in the previous two videos I have made it very clear what exactly the directional coupler is. So it is a coupler, so it couples the energy from primary waveguide to secondary waveguide. So these are the two waveguides into the directional coupler. So primary waveguide running from port number 1 to port number 2, and the secondary waveguide running from port number 3 to port number 4 here. Now in between the side walls for the primary waveguide and that of the secondary waveguide, so this is the primary waveguide and this is the secondary waveguide, we have the coupling made possible with the help of holes here. So either there can be one hole, there can be two holes, or there can be n multiple holes here. So because of which whatever the input power we have fed to the port number 1, it will have leakage into. So one branch will be going towards the forward direction, one towards the backward. Again we can have here the leakage at hole number 2, it will have the forward direction and a backward direction. So the backward direction branches are cancelling out each other because of the 180 degrees of phase shift if we have the distance of separation denoted by capital L, and it is twice n plus 1 times multiple of quarter guide wavelength here. So because of 90 plus 90, 180 degrees of phase shift occur. So this all working of the directional coupler, especially for the two-hole directional coupler, we have gone through. Now let us have the derivation for scattering matrix. So scattering matrix is generally represented by S matrix. In the matrix form we can show the two square brackets, so inside it is capital S here. So there should be the order of the matrix to derive. So order of the matrix, it means how many number of rows are there, how many number of columns are there. So the order of the matrix depends on the number of ports. So in this particular diagram you see here it is port number 1, port number 2, port number 3 and the port number 4 here. So total 4 ports will be there, therefore the order of scattering matrix will be 4 by 4 here. So let us derive the scattering matrix. So initially we represent the scattering matrix S in matrix form. The 4 rows and the 4 columns, the total 16 coefficient will be there, and these totally will be unknown to us. So therefore the generalized representation, it will be for the first row coefficients S11, S12, S13, S14. For the second row coefficients we have S21, S22, S23, S24. For the third row coefficients we have S31, S32, S33, S34, and for the last row coefficients we can name them S41, S42, S43, S44 here, and we complete the square bracket here. So let us have this generalized representation of scattering matrix for the directional coupler of the order 4 by 4 represented by equation number 1 here. Now for the directional coupler, we know that all the 4 ports are perfectly matched to the junctions. So therefore we can have the scattering coefficients out of the 16 here. that is S suffix 1 1, S suffix 2 2, S suffix 3 3, S suffix 3 4. So these all will be equal to 0 here. So S11 equal to 0, S22 equal to 0, S33 equal to 0, S34 is equal to 0 here. So this should be S44 actually. So now you can see here, perfectly matched to means what? Perfectly matched means if we have certain port with the impedance denoted as Z, and the transmission line, which is basically a rectangular waveguide, whatever the arms we have in the directional coupler are from the primary and the secondary waveguides. So these are the transmission lines, and for a transmission line the characteristic impedance is denoted by Z0. So when we have the load impedance or the general impedance at the port equal to that of the characteristic impedance of transmission line, we can say it is the perfectly matching here. So therefore we make these four coefficients to be equal to 0. Why make these four coefficients only? You can see here in the subscript the same number repeats here, S11, S22, S33, S44 here, because in general when we write S suffix ij here, this is the input provided to the ith port and output taken at jth port. So S11 means it is the scattering coefficients when the input is provided to the first port and output is also taken from the same port. So if we have the perfect matching, so that time there is no reflected waves generated, so no chances of having the standing waves. So in that case, when input is provided to the first port, it will not reflect back any of the output, hence S11 is equal to 0. The same is the case for port 2. So input at port 2, output also at port 2 will be 0. Input at port 3, output desired at port 3 will also be 0. Input at port 4, output desired at port 4 will also be equal to 0. Hence, out of the 16 unknown scattering coefficients, we can take the four coefficients S11, S22, S33, S44 replaced by zeros here. So the number of unknowns have been reduced from 16 to that of 12 here. Now in addition to that, in the third topic of this chapter, we have gone through the understanding of the scattering matrix theory, scattering parameters theory. So that time the properties of scattering matrix have been addressed. One of the property there, it was the symmetric property. So according to the symmetric property, we have S suffix ij nothing but S suffix ji. The meaning is that if we have input provided to the ith port and output taken at jth port, so whatever the reflection relationship between the input output will be there, it will be the same magnitude if we have the input provided to the jth port and output taken at ith port. Hence this is the property. So as we have four ports for the directional coupler, we can make the various combinations to be equated for the symmetric property given as S21 will be nothing but S12, S31 will be nothing but S13, S41 will be nothing but S14 here, S32 is nothing but S23, S42 will be equal to S24 and S43 will be equal to S34. So all these replacements we have to make changes into the earlier representation for equation number 1 there. So we have to prefer the lower order combination here. So instead of S21 we can go for S12, instead of S32 S23 here. S13, S24, S14, S34 will be preferable as compared to their higher order combinations here. So if we represent the perfect match condition for the junctions represented by the values of four coefficients like this to be equation number 2, in that case, due to the symmetric property, what we have the replacements to be made for the lower order preference of the scattering coefficient, we get it represented by equation number 3, and we can have the changes into the equation number 1. Now in addition to that, as we know the structure of the directional coupler, the pair of ports, port number 1 and port number 3, are isolated ports, whereas the pair of ports, port number 2 and port number 4, are also isolated ports. So therefore we can make the scattering coefficients s suffix 1 3 and s suffix 3 1 to be equal to 0 here. So let us see this representation. Because the pair of port 1 and 3 or 3 and 1 are isolated ports, these two values should be equal to 0. Port 2 and 4 we have just now talked about, these are also the isolated ports. Therefore we can write s suffix 2 4 is equal to s suffix 4 2 is equal to 0. So these two scattering coefficients can also be equal to 0. So we have this representation by equation number 5. The meaning is that there it is no connection from port number 1 to port number 3. So while we can provide input to port number 1, there it won't be any output at port number 3. There it is no chance to provide port number 3 the output, but though if it is possible to give the input to port number 3 the input at, we cannot have the output to port number 1. The basic mechanism we have seen, so it will be cancelling out of the signals due to the phase shift of 180 degrees. Similar is the case if we reverse the directions from port 2 4 to 1 3 here. Now we can further make the use of these equations 2 3 4 and 5. So therefore I can write here, using equations 2 3 4 and 5, equation number 1 will imply. So according to the equation number 1, what it used to be scattering matrix S of the order 4 by 4, the first row in the modified form, it will be S11 will be equal to 0, S12 as it is, S13 because of this equation 4 it will be 0, S14 will be as it is. In the second row, S12 will be the same instead of having S21 because of the symmetric property here. In place of S22 it is 0 due to the perfect matching. In place of S23 as it is, in place of S24 it will be 0 due to equation number 5 here. In the third row we have S31 equal to 0 due to equation number 4. S32 can be replaced by the lower order combination from the symmetric property S23. S33 will be equal to 0 due to perfect matching of the junction from the earlier equation, and S34 can be the same here. In the fourth row we can have S41 replaced by S14 due to the symmetric property. S42 can be equal to 0 due to equation 5. Now S43 can be replaced by S34 and S44 due to the perfect matching to the junction, we can substitute by 0 here. So this new representation where we have more reduction into the number of unknowns can be for the scattering matrix given by equation number 6, the next equation number here. Now let us make the use of unitary property. Now according to the unitary property, when we have the scattering matrix S in multiplication to its complex conjugate, so for complex conjugate representation we put asterisk over the head of scattering matrix. So this multiplication of the two matrices produces the identity matrix. So identity matrix, it means that all the coefficient values into the matrix are zeros except at the diagonal places which are having the values unit. So unit means the values 1 for the diagonal elements and rest of all others are equal to 0. So therefore according to the unitary property we represent the scattering matrix from the previous equation. So this will be 4 by 4 order, the first row 0, S12 0 S14, S12 0 S23 0, 0 S23 0 S34, S14 0 S34 0. Multiplication to its conjugate representation. So the first row it will be 0 S12 conjugate 0 S14 conjugate. Second row it will be S12 conjugate 0 S23 conjugate 0. The third row it will be 0 S23 conjugate 0 S34 conjugate here. Whereas the last row is S14 conjugate 0 S34 conjugate 0 here. So I complete the square bracket for the matrix. Now the multiplication of the two has to result the identity matrix. So if this is 4 by 4 order, its conjugate is also of 4 by 4 order, the identity matrix should be of also 4 by 4 order here. So in the first row we have 1 0 0 0, in the second row 0 1 0 0, in the third row 0 0 1 0, in the fourth row 0 0 0 1 here. This is also of the order of 4 by 4 here. So let us denote this equation by equation number 7. Now for the matrix operation onto the left hand side, basically the matrix multiplication, we can have the operation represented R1 C1. So for the first matrix we can take first row, and for the second matrix we can take the first column. So in that way, when we have the multiplication first row first column, we have the value in the RHS at this place, first row first column element, the value is 1. So it will give us the equation from this equation number 7, that it is mod of S12 squared mod of S14 squared. So these two are the additions, and resulting it will be into the 1 here. So we have S12 into S12 conjugate, the addition, the multiplication of the two will be a mod square here. S14 into S14 conjugate, this is represented as S14 mod squared here. So this will be the next equation number 8 here. In the similar fashion, instead of having R1 C1, if you make R2 C2, so in that case we come to have the another equation in the form mod S12 squared added to mod S23 squared. So this is equal to 1. So this it will be the value. So this is equation number 9 here. Next to that, if we have R3 C3, so this implies to the equation in the form S23 mod square added to S34 mod square. This is equal to 1. Equation number 10 it is. Next to this equation number 10, if for equation number 7 we perform the matrix operation for multiplication R1 C3, so it implies to the form of the equation S12 can be multiplied to S23 conjugate, and this is added to S14 multiplied to S34 conjugate. So this is equal to 0. So this is the next equation number, equation 11. Now if we have a comparison of equation number 8 and equation number 9, we come to have a conclusion that S14 is equal to S23. These two terms should be the same, then only we come to have this particular equation 8 and 9 truthful here. So I write here comparing equations 8 and 9. So this finding from this comparison can be regarded as equation number 12 here. Further, we can make the comparison of equations 9 and equation 10 here. So this results into the finding that S12 should be equal to S34 here. So this finding is regarded as equation number 13 here. So now if we let the scattering coefficient S12 is real and positive. So that time we have S12 which is equated to S34 earlier. This will be equal to small p, and this is nothing but S34 conjugate also. So let this can be equation number 14. So because of this representation, the equation number 11 therefore will imply to the information that p in place of these in multiplication to S23 conjugate added to S14 times small p will be equal to 0. So therefore, next using equation number 12, we can have the finding p into S23 conjugate added to S23 into p is equal to 0. So therefore, we can take the p common from the left hand side. So p in the bracket we have S23 added to S23 conjugate. This is equal to 0. Now for the equation number 14, we have the assumption that the p is real and positive. So p cannot be equal to 0. So therefore for the above equation, we have to take S23 added to S23 conjugate is equal to 0 here. So here we let that S23 is a real part, this is the conjugate part. So therefore S23 is equal to J times Q. So this implies that S23 conjugate will be minus J times Q here. So where small q is real and positive. So the representation of S23 JQ and S23 conjugate minus JQ. So this we can represent by equation number 15 here. Now whatever the scattering matrix we had represented into the equation number 6, by the use of the recent equations we can represent again. So now I write using equations 12, 13, 14 and 15. We have the equation number 6 giving the new representation. The scattering matrix capital S of the order 4 by 4 is equal to, the first row is 0 P 0 JQ here. The second row is P 0 JQ 0. The third row is 0 JQ 0 P, and the fourth row is JQ 0 P 0 here. So I complete the bracket here. This is 4 by 4 order scattering matrix for the directional coupler here. So we can derive up to this particular point for the directional coupler, which is a 4-port microwave component passive type here. So this is the required scattering matrix, S matrix you can say. So based on to the knowledge in the recent videos for the directional coupler and this one, by the next lecture we shall be having a practice of simple 2 problems based on directional couplers here. So stay tuned to the Ekeeda channel for more such information and the knowledge if you want for microwave engineering subject. Thank you.